Really quick. So if I'm looking at this problem, I'm going to go and have to take care of part A first. It says find all of the choices of A and B such that f is continuous at x equals 1. Well, so if f is continuous at x equals 1, and I know we have a quick way we can do this, right? But I'm really going to kind of show the big idea behind it. We would know that the limit of f of x as x approaches 1 from the negative side would have to equal the limit of f of x as x approaches 1 from the positive side. And this also has to equal f of 1, right? But f of 1 is already covered inside of, the limit as it's coming from the left, right? Because 1 is actually included in there. So in other words, I know that really, I'm looking at what's the limit as x approaches 1 from the left of a of x, ax, right? You can't really tell that that's a 1. What's the limit as x approaches 1 of ax? A, right? I mean, ultimately, we're just looking at what's that function going to become, right? So we really kind of just plug in the 1 because what it's becoming is what it becomes, right? Although it doesn't actually become it. Well, it does become it in this case. So that's really A. Then I'm going to do the same thing on the other one, right? I'm now looking at from the positive side. And, so I can just put all that stuff right there. And what's that going to become? B plus 2. I see this, I don't see this. All right, so we know that it's got to equal B plus 2. So, if B is 1, A must be 3. If B is 2, A's got to be 4. There's lots of choices here for this to be continuous. They just have to have this relationship. There is not a singular A and B to make it continuous. And this most likely is due to the fact that, if you think about it, I could take each of these functions, make them match up, and then I could just do this. Actually, I could stretch one of them and then kind of shift the other one. But there's lots of ways we could change them, and that's what's happening here. All right, now, here comes the actual question. Find all of the values A and B such that f is differentiable. What does it mean for f to be differentiable? What does it take in order to be differentiable? No. No. Yes.
It needs to have the same limit from both sides. It needs to have a two-sided limit that exists.
No sharp point must be continuous. Well, guess what? We already took care of this. I know that has to be true. Part A was continuous, asking about continuity. So I know that this has to be true. And that only gets us continuity. So what the heck is this no sharp point thing? I mean, think about what that looks like for a second. No sharp points. That means it doesn't look like, we'll do pink is bad. It means it doesn't look like this. It means it doesn't look like this. What does it mean for it not to have a sharp point, besides the fact that it doesn't look like that? Judy?
The derivatives need to approach each other.
This derivative, this slope, has to be coming and blending directly into that slope. The slopes at that spot really need to be approaching one another. The slopes at that point, loosely, I'm going to say, need to be the same, right? There's one slope, I'm coming at a slope of 2, and then the other one starts at a slope of 2. And that would look good, right? If one's coming at a slope of 2 and the other one's coming at a slope of -2, all of a sudden it's sharp. Right? But if I can make the slopes match, I'm good. I did this painter on my WTI. I didn't do that. Okay. So in order for us to get this, we need, and I'm going to, actually, let's do this. So no sharp points. So I need the slopes to approach each other. Or again, like I said, I need the slopes to be roughly equal, right? At 1. At x equals 1, I need the slopes to be equal. So then what's the slope of the first piece? Or actually, let's go ahead and get the slope function. F prime of x equals. What is it? A. And not like UPA, like A. A? No? All right, that's fine. What's the slope of the second piece? 2bx plus 1. And so this is when x is less than 1, and this is when x is greater than 1. Now, I'm interestingly leaving off the equivalent to 1 because I don't necessarily know that they would be the same. I'm going to make them the same, but, right? No big deal. This is just short-term work. I need those slopes to be equal at 1. So I really need this to happen. I need A to be equal to 2b times 1 plus 1. I'm good? Not good. Cool. Now it's just algebra. Let's get rid of all this junk. I think I got everything written down. So in order for the function to actually be differentiable, I need not just one thing, but two things. I need both the white and the green, which I'm going to go ahead and simplify the green. It really says A equals 2b plus 1. I need both the white and the green to be true. I need A to be equal to b plus 2, and I also need A to be equal to 2b plus 1. Yep. Looks like a system of equations to me. Use substitution. I think that's probably the easiest way here. So I'm going to go ahead and say, I really want b plus 2, which is really A, to be equal to 2b plus 1, which is really A, because I want A to equal A. And then I can go ahead and solve that. And when we do, we get what? B equals 1. And then once we've solved for b, we can get A equals 3. This is the only choice of values that will make it so that it's both continuous and so that the slopes blend nicely into one another. So that makes it continuous and differentiable, or just differentiable, because that relies on continuity. Questions on this